All right, today we're diving into something that sounds like it's straight out of science fiction. Topological quantum computing. It's all about the hunt for a truly unbreakable code. So, let me ask you something. What if a computer could be, well, immune to errors? Just imagine it for a second. A type of computing so rock solid that all the usual static and noise that messes with our best systems today just couldn't touch it. I mean, that's the massive promise we're talking about here.
And that brings us right to our first big idea, the unbreakable code. Look, this isn't about making a slightly faster or better computer. No, this is about a totally new way of thinking about how computation even works.
Okay, so here's the real kicker. The goal of topological quantum computing is to build a machine that basically protects itself. The information is safe by design. It's built to be fault-tolerant from the get-go, which, if it works, would leapfrog the biggest problem everyone in the quantum world is trying to solve.
But to really get why this is such a game changer, you have to understand the problem it's trying to solve. Let's talk about what I like to call quantum's fragile genius.
The quantum computers we have today, they're amazing, seriously powerful, but they're also super delicate. The fundamental building blocks, the qubits, are kind of like soap bubbles. The tiniest little vibration or change in temperature, what scientists call decoherence, can just pop, and your whole calculation is gone, just like that.
So this really shows you the two different worlds we're talking about. On one side, you've got your standard qubit. All the information is packed into one tiny local spot. Super fragile, right? But on the other side, you've got the topological idea. Here, the information isn't in just one place. It's spread out. It's non-local. What that means is, if one little spot gets disturbed, it doesn't matter. The whole message is still safe. It's just naturally protected.
Okay, so how on earth do you achieve that kind of protection? Well, the answer, believe it or not, comes from a really elegant area of math that you'd never expect. This is where we get into the secret of shapes.
The secret ingredient here is something called topology. And I know, it sounds complicated, but don't worry. The basic idea is actually pretty simple. Topology is just the study of what stays the same about an object when you squish it, or stretch it, or bend it all out of shape, as long as you don't actually rip it.
And there's a perfect classic example to show you exactly what this means. So, to someone who studies topology, a coffee mug like this one is, well, it's the same thing as a donut. Seriously. And you might be thinking, how? It's because they both have one single hole. And that property, the one hole, is incredibly robust. You can't just squish the hole away. You'd have to physically tear the object to change it. That unchanging property is the whole secret behind topological protection.
Okay, a coffee mug is a donut. Cool. But how does that help us build a computer? Well, this is where it gets really weird and fascinating. We're going to see how scientists are literally weaving with weird particles.
The main players in this story are these strange, exotic things called anyons. Now, they're not quite particles in the normal sense. They only show up in super flat 2D worlds. And here's the wild part. They have a kind of memory. Their quantum state actually keeps a record of how they've been moved and woven around each other. And if you're wondering how you even make these things, one of the top candidates is another bizarre character, the Majorana fermion. This thing is so strange, it's its own antiparticle. It's a huge deal in physics right now for exactly this reason.
So how do you actually compute something with these? Well, it's basically a four-step dance. First, you create these anyons in pairs. Then, you encode your information across them. Remember, it's non-local, just like the hole in the donut. Step 3 is the craziest part. You physically move them around each other, weaving their paths together to create what's called a braid. And finally, the answer to your calculation is right there in the overall shape of that braid. You just read the topology.
And this is really the mind-bending part. The computation isn't happening inside the anyons. The computation is the braid. Every time you loop one around another, that's a calculation. That's a logic gate. And because the final answer only depends on the overall pattern of the weave, the topology, it doesn't matter if the paths get a little wiggly or noisy along the way. The result is protected.
Now I know this all sounds absolutely incredible, like we've solved it, but we gotta be real here. This is still very much cutting-edge experimental stuff. So let's take a look at what the road ahead actually looks like.
And yeah, the challenges are huge. For starters, just creating these anyon systems and keeping them stable is a massive hurdle. Then, you've got to control that braiding process with insane precision. And of course, the big one, how do you scale this up from a cool lab experiment to a real computer with thousands or even millions of these qubits? It's a tough road.
But the potential payoff is so enormous that the big players are all in. You've got companies like Microsoft, plus all the top university and government labs, and they're all in this high-stakes race to crack these problems and be the first to build a truly error-proof quantum computer.
Which really leaves us with this one huge question. After all this time struggling with how fragile quantum states are, is this the answer? Have we finally figured out that the trick isn't to fight the noise, but to use the fundamental geometry of the universe to protect our information? Could weaving the fabric of space-time itself be the key that unlocks everything? It's a wild thought, but the answer? Well, the answer could literally change the world.